look at least squares problems. I think the last time I just introduced it, but we didn't get into the details of it. So we'll look at least squares problems, which, as I mentioned, are probably one of the most commonly found problems in engineering. So there is linear least squares and non-linear least squares. We'll look at both. And once we're done with that, the next part of the course will be constraint optimization, which will start after the quiz. Okay. All right, so let's look at least squares optimization. In terms of motivation, we don't need to re-motivate it. We had given two models, if you remember. What was the first model? There was radioactive decay, right? There was one model. So let me just write that one example down. So this was example one, was something like this. Right. So over here, what was our T? Was our measurement time. And what would we call X? In plain English, what would you call X? Parameters of the model. And the other model that we had was, for example, something simple like this. What is the difference between these two models? In terms of nomenclature, the first model would be, it's non-linear in the parameters, right? So this is a non-linear in the parameters, and this is linear. Loosely speaking, we call it linear, but technically, what should we call it? Affine. I mean, there could be a constant also over here, which I have not mentioned. Okay. So these are the two broad families of problems. Once you have got a model, the model is not going to come to you from optimization. The model is going to come to you from your domain knowledge. Okay. And as I mentioned in the very first lecture, this is where your modeling accuracy comes into play. Okay. Having done this, we had written the problem in the following way. What is the problem to be solved, right? So we said, let us say I take m measurements. For each measurement, I have a model and I have the model's prediction. And this I have to try to what? Bring as close to each other as possible, right? That's the basic idea. So if the measurement is, let's say, some yj, correspondingly the prediction is going to be, right? This is my, you could say, my jth measurement. And what I'm going to do is I'm going to square this. J is going to go from 1 to m, right? And this is what I want to minimize as much as possible, right? So what is the tuning knob in my hand? I mean, it's a very basic question, but you will be surprised at how often students get tripped up in this. What is the tuning knob in my hand? X. So I will write this as this argmin x. This just tells me that x is the variable of optimization which is in my hand, and out after I solve this, x hat. X hat here means it's the best x, right? Okay, and so this is why we call this a least squares optimization. So least. I think we had spoken roughly until this point. Now to progress any further, we obviously need to know some, or not know, but do some calculus on this so that we can take derivatives, set them to 0, look at second derivatives and so on. Okay. So there is a, because these problems occur so frequently, there is a standard terminology for solving or mentioning most of this. So each of these, so let me just make a mention over here. This is total number of measurements. Okay. Is there a common word that we use to denote the expression inside this red bracket? in the optimization world, this expression within the red bracket, what do we also call it as? Not quadratic, a general word, objective function. Objective function, or another very common word is cost function. Okay, so cost function. In many papers, you will in fact see this written as C dot F, and you will wonder what does this C dot F. It just means cost function or objective function. Okay, and the common symbol for it, let us say, let's call it f of x. Now, when I say f of x, you should realize that x here is a vector or a scalar. It's a vector because there can be many parameters in the model. Okay. So, the common way of writing this expression is this one term over here is called a residual. So, let us say yj minus y of x comma j. I am going to call this a residual. Why residual? Because that's the residue left when I match my data with my prediction. Okay, and the common notation is this rj of x. Okay, so if I have all of these residual quantities are there for each measurement, I have these residuals. I can as well stack it and make a vector out of it. Right. So the residual vector then it simply has the expression r. Okay. So r of x is going to be a vector. So r1x up to rmx, because there are m measurements, and transpose. Okay, and the common expression is written like this. Okay, so j is equal to 1 to m rjx. This half is introduced just to make math a little bit easier. Otherwise, you'll have a 2 floating around everywhere. So don't worry too much about it. Okay. Now, how many? Obviously, I'm going to call x as an n-dimensional vector. So x is Rn, right? So let's look at the numbers over here. If I have m is greater than equal to n, okay. So here is where we need to first operate from common sense. M greater than equal to n means what? I have more measurement than variables. Is that, from a common sense point of view, is that a good place to be or a bad place to be? It's a good place to be in, because you have enough measurements are there. I mean, if I have like 10 parameters of the model and one measurement, and there's that famous saying, I don't know who that physicist is, that if you give me 3 points, I can fit an elephant for you, right? So any model will fit it if I have less data and too many parameters, right? So this is where you want to be, and this is also the more realistic case. Right? What about this? There may be some situations where data may be extremely expensive. For example, I mean, with the Geiger counter, right? Radioactive measurements, you cannot send a person to make too many measurements, so you have less number of measurements, right? So there are situations when this also happens. This is more challenging, and the uniqueness of the solution, all of these properties are questionable. Okay, so in principle, this is the situation where you can have infinite solutions. Okay, when you have infinite solutions, then some solutions come with some special properties, right? So okay, let's take a very simple case, something that you have all studied from class 11. When you have a linear system of equations, right, that means a fact matrix. Fact matrix has infinite solutions. Is there any special solution out of these infinite solutions? I have infinite number of solutions, that everyone agrees on, but is there any one solution which has a special property? There's a minimum norm solution that is possible. Of all the solutions, you can find one solution which has minimum norm. Okay, minimum norm, and we'll discuss this at the end of this class when we look at linear least squares. Is there any, from an engineering point of view, is there any special appeal for a minimum norm solution? Minimum norm can often mean minimum energy. So that has a desirable aspect to it. So even though you may have infinite solutions, you may still be able to arrive at a minimum norm solution. That minimum norm can be, for example, minimum energy for a physics application. For some sensor network application, it may be minimum power of the nodes, whatever, right? So those solutions are still possible. There is another very interesting area of research now. It's about, I would say, 10 to 15 years old, which is called compressive sensing. Which is a very beautiful subfield of signal processing, where you can show, there are theoretical guarantees for this, that you, in spite of m being less than n, you can arrive at a unique solution. Okay, it's so this is a very nice possible topic for your course project. Okay, many students in the past iterations have enjoyed this topic. So just telling you, it's very counterintuitive, but it's good fun. But for now, this is the case that we're going to look at, okay, where common sense dictates there is more measurements than the number of variables over here. Okay. So with my residual vector r defined this way, is there yet another very compact way of writing this cost function f of x? Instead of this laborious summation that I've written, can I write it in some other way? Half norm r square, right? L2 norm. So let's look at these two objects over here. So I have at the top over here. Now r of x, is r of x like a function also? Does it take an input and give an output? So what is the input? Dimension of the input? N. N variable x enters into this guy. What comes out of it? How many measurements do we have? M, right? So it's a vector, right? Similarly, f of x, that's our objective function or cost function. What does it take as input? Rn comes in and out comes simply r. Right? So which one of these guys is going to have a Jacobian, a non-trivial Jacobian? It's going to be r. Right? Now finally, when I'm looking at f of x, which I've written over here, I want to, if I want to calculate a stationary point of f, what am I going to be looking at? Given f, you want a stationary point. What is the quantity that I need to look at? Grad of f, right? Now, grad of f, because f is written in terms of this r, it'll make our life a little simpler if we look at, anticipate that what's going to happen when I start differentiating f with respect to x1, x2 up to xn. I'm going to see a norm r square that's going to appear everywhere. So before we jump into grad f, let's just look at the Jacobian of r. It will help us simplify the math, because I have to take a derivative of r anyway, and a derivative of r is also known as Jacobian. So let's look at yeah. So remember, we had a, if I give you a function f and I ask you grad f, it was a column vector like this. Everyone remembers this. But when I gave you a function like r, which is rn to rm, how did we write the Jacobian of r? Sorry, small r. There was a transpose operation, if you remember, right? So every row of the Jacobian was what? Grad of each of those residual terms, right? So let's write down now. Okay. So is this right? Right. So I have J I. So J is now the row, I is the column, right? So if I'm keeping the row number fixed and I'm changing the columns, right? I'm getting grad R1 is one row, grad R2 is one row, right? So if you visualize it, it's like this: grad of R1 transpose. So it's going like this. Grad of R2 transpose is going like this. So that is how my matrix looks like. Okay. And if you wanted it further explicit, R1 by dx1, R1 by dx2. That's how it looks. Okay, so you already know f of x is equal to, we're going to write it in a simpler form, half of rj x squared. Okay. Now I want to calculate grad f, right? For calculating grad f, what is the one thing that I need to do? Calculate, for example, df by dxi. Right? So I can take this expression over here and start differentiating j equal to 1 to m. So one common mistake, again, a lot of times students make is that mixing up the variable of summation and the variable of differentiation. So here the dummy index for the summation is j, right? So I should take the derivative for, I mean the subscript for x should not be j, because I will land up into, that's why I've taken I over here. Very common mistake, but it messes you up. So right, so if I take this derivative, what happens? I'm taking the derivative of this expression over here. What happens to my 2? 2 goes away, right? So this is, will the summation still be there? Has to be there, because each r depends on all the x's, so it's going to be there. So this summation remains there. Okay, I have a rj of x and I have a drj by dxi of x, and I can just, for simplicity, rearrange them this way. Now this is df by dxi. I like this. I want from df by dx1, x2 all the way up to xn. What is this guy reminding you of? It's looking like exactly like the term of the Jacobian here. It is the, it's looking like the jth column, right? And I have a rj over there. So is there a nice way by which we could simplify this expression? It is looking like the column of a, I mean, you look at j is the guy that is varying in this expression over here. J is the variable of summation, I is remaining constant. Okay, so over here in, if I is remaining constant, which is x, that is corresponding to, for example, let's get blue over here, one column like this. Because over here, what is changing? R1, R2, R3, but x2 is remaining the same in that. So it's a column of my Jacobian matrix. So I'm multiplying the column of a Jacobian matrix. But when I multiply a matrix with a vector, what do I multiply? A row of the matrix with a column vector. So this is not exactly like that with J, but it's with J transpose. If I take J transpose, this blue circle thing will become a row vector, and that is getting multiplied by which vector? R. Its components are there, Rj, R1, R2, right? So this is, so this will simply be J transpose multiplied by R, right? If you want it to be a little bit more explicit, you would call this, because they're all functions of x. Okay. So this is why we spent like 15 seconds trying to compute this Jacobian, because it shows up very neatly over here. If I didn't have this, I'll have to write this partial summation, this summation with partial derivatives, carry it forward everywhere. At some point, I'm going to interchange a j and I, and my answer is going to go wrong, right? So this has kept it, neat. So that I've got my expression for grad f. Any questions on this? Anyone not clear on it?